Okay, sorry. Yeah, so let's say we're looking at hydrogen. It will have one proton in the center, and hydrogen will have one proton in the center there, but it will also have a neutron. Ne? So proton and neutron, they have to exist together to form the nucleus of an atom. And that nucleus of an atom, its mass, ne, is accounted for in the approximate relative atomic mass. And now it's almost double the atomic number in many of them. You look at hydrogen, it's 1 1, but you go to helium, it's 1 2, it's 2 4, sorry. You go to lithium, it's 3 7. So Avona, it's almost just a bit above twice. Beryllium, I believe, 4 9, 5 11, carbon 6 12. And that's because carbon is one of the most abundant life substances in the world, in the planet, in our existence. I guess planet and maybe much of the universe. Let's say that, né? A lot of the universe, at least with material things we can see and touch in. And then it's also part of our DNA, our bodies, these plastics, etc. It's very abundant. You're not at least in substance, and nitrogen in the atmosphere is the most abundant, and water, oxygen. But these ones, I believe their numbers are almost double because they are those ones we are readily accessing. Nevertheless, hydrogen will have one proton and one neutron. Those two are called nucleons because they form a nucleus. So nucleus, you think about it like in an animal or plant cell, is that thing inside the cell that's the center of it and kind of controls everything within the cell. So you could think about it as maybe your brain and heart combined. Yeah, maybe your brain and heart combined, because those two have to work together so that you are always alive and doing things. So that's nucleus. And then a bit far away from nucleus, well, actually much far away from nucleus, ne, is where you get your orbitals. Orbitals give a space where your electrons in an atom move. Right? Now these orbitals, that's where your electrons move. Ne? And a lot of the scientists who came up with the theories about how atoms work, they came up with these, including Chavo, where the nucleus is it in the center of the atom or is it Katu? So we know now that it's in the center. So all of that knowledge, we do it in grade 10. Why is it important? Because in the same atom, we've got protons and electrons. And when I learned electrostatics and we have the magnitude of charge. Okay? Is it 10 to the power negative 18 or 19? 19 coulomb, yeah? That's the magnitude of charge. But the same magnitude, yeah, on a 1.9 times 10 to the negative 19. For proton, about positive 1.9 times 10 to the power negative 19 coulomb. So these are the same kinds of charges you play with in electrostatics. Because when you calculate a charge AJ, and then you have to use these in the calculations. So those charges, they come from atoms themselves, and atoms you find anywhere. So anything here that you can think of is lightly electrically charged because of these electrons. Secondly, these same that's why acids and bases are electrically charged. These electrons are the ones that get exchanged during acid-base reactions. So that is why acids are electrolytes in solution, because they according to the same theory, Arrhenius, they often exchange electrons so that atoms in the molecule that are electron donors can give up they can give up electrons and others can receive those electrons. And that's where this thing here, Bronsted-Lowry, the theories come as well, where we look at things that donate protons, etc. But it's only in relation to when these substances are, it's just the pure diluted in water. That one. So within the water, how does it react? That one. So that explains electrolyte. So we took it from concept atom and where electrolyte comes from. Electrolyte comes from because every atom in a lay electron then it's able to transfer some kind of charge. Yeah. Ne? And then I also wanted to share the same electrons also govern how and why electrons would bond with one another. Because M1 would be willing to receive an electron and would be willing to donate it. But those are the basic things that happen that exchanged in a reaction. And then secondly, a polar solvent. Ne? Most soluble salts, sodium chloride, and in sodium Elia plus and then the chlorine Elia minus. That's in when you are doing electrolytes further in the chapter. Those are soluble salts. So sodium chloride, potassium chloride, magnesium chloride, those kinds of salts. That one. There's acids, hydrochloric acid, I guess ethanoic acid. Or maybe let me not say ethanoic acid because it's an organic acid. So, but I guess it also behaves the same. It's a weak acid. But nevertheless, acids, bases, also sodium hydroxide, etc. All of them donate share the electrons and they donate protons and stuff. Right? And this happens in a polar solvent such as water. So now the polarity, the substance such as water becomes important here. Ne? For two reasons. Ne? For two reasons. Ne? Okay, maybe for a number of reasons. But I'm just gonna mention a couple of them. The first one here, hydrogen on our periodic table, it's on the group of metals, ne, that donate electrons. So they would typically donate like 1 electron. But the next group, group 2, would donate like 2 electrons. Group 13, which you can think about as group 3, if I include JQ groups 2 to 12. That group, they tend to donate 3 electrons. The fourth group, carbon, tends to either donate or receive 4 electrons, depending on how it's reacting. Nitrogen tends to receive 3 or donate 3, depending on how it's reacting. Oxygen tends to receive 2. Fluorine receive 1. JK, the noble gases, they dish up. So because of that thing, I'll exchange that electron. Let's look at okay, so we're still explaining electrolyte, right? So polar, they said what? Polar solvent. Solvent is a substance that you use to dissolve other substances in. Alright? So like you can dissolve fats in alcohol if you did food tests, more life science, where you test for the presence of fats in the food, for the presence of I guess sugars, for the presence of, you haven't done those? Haven't done food tests? They took out food tests from syllabus of life science? Yeah. Okay, fair enough. Nevertheless, the atom, let's say we've got hydrogen. And then we've also got an oxygen. I could write H2O, get the formula, the chemical formula for water, right? It's 2 hydrogens per oxygen. So you've got 1 hydrogen there and another there and an oxygen there. The reason why water is a polar solvent is because hydrogen would donate an electron. So hydrogen donates electron and then it gives you H+. And then when oxygen receives electrons, when oxygen receives electrons, and then it becomes oxygen 2 minus, ne? So once hydrogen gives up its electron, it gives it up to the oxygen, and then in the orbital, remember the orbital where the electrons move, in Lewis diagrams, it looks something like this, right? So there's your electrons jump, oxygen, and then there's space for one more there, and there's space for one more there, because that's how electrons get transferred. Now, hydrogen has only one electron, so it will give up one electron and it will bond with the other electron there to make an electron pair, and then the other hydrogen will do the same with the other electron if free. That way, you end up having an H2O molecule, which looks like this. And this combination of these specific chemical elements gives them a polarity. Why? It gives them a polarity. Now, because oxygen receives electrons, it becomes even more negatively charged. So its charge becomes negative, even in the negative, minus. So it becomes negative on this end here, but closer to the hydrogens, it becomes positively charged. So now, because of this, every molecule emanates inside water is like this, right? There's a one end where it's positively charged and the other end that's negatively charged. Now, because of this, when you dissolve in acids, salts, acids and soluble salts, acids and bases in water, when you dissolve it in that, that's why that's why, not secret, because they're not the same. The one is organic, sugar is organic, sodium chloride is inorganic, and acids, bases, and electrolytes are inorganic. So salt. Put salt in a cup and you stir, it dissolves. That's how I go on. But what happens is it kind of goes into an electrolyte phase. And that electrolyte phase makes us not see the crystals anymore because it's soluble. So now what happens is, the sodium particles, the sodium ions that become positively charged because they donate electrons, they become in ionic form. Remember, medium with ions. So when you take sodium chloride, and then it becomes sodium, this one having given up an electron and this one having received it, yeah? Then what happens is, agriona is so, let's say it looks like this, né? There's our chlorine, there's chlorine there, and then here we've got sodium, né? So here we've got sodium and then we've got chloride. So once it dissolves in water, what happens is the sodium, because it's positively charged, moves closer to the oxygen, where it's negatively charged, the negative pole of the water molecule. And then the chlorine, because it's negatively charged, it gravitates, or rather moves closer to the positively charged part of the water molecule. So you'll find your chlorine would be somewhere this side, and your sodium would be somewhere closer to the oxygen. I'm not sure why it's not showing the things there. Okay, so I guess you needed to be refreshed. Yo, Jambo, we understand. understand you're going away there, Muna. But if I refresh here, what happens? Because I've just refreshed the app on the device there. Yo. Or let me just do this. Could you move this one specifically? Yeah, this specific one. Open that up, open it up again. Yeah. Ne? So the chlorine would be gravitating to the positive pole of the water molecule, and the the sodium would be closer to the negative pole of the polar solvent. Polar solvent. So polarity. Udile, what's geography? Geography. So you do. But solar one a magnet, one north, one south, and the other end. And then the one pole, or the levancha, so they attract, and the other poles are the levancha, so they repel. So the ones that are close to each other, the ones that are similar. For now, what we're taught is, because chlorine is negatively charged, is attracted to the positive pole of the water molecule. Just like the North Pole would be attracted to the South Pole of another magnet, that type of thing. That's how science today explains it. Ne? So, because we have, or rather explain that, yes, we need to now go to the next thing about the difference between acids and bases. So you understand where electrons come from, like, and then the relationship to solvents and water, etc. And now this thing here, the ion, ne? Right, so acids increase the H plus ion in solution, right? In solution. But bases decrease the H plus concentration in solution. So in other words, H plus in a solution, means it's been dissolved. The acid has been dissolved in the water, or the salt has been dissolved in the water. That's what in solution means, ne? So in solution equals substance has been dissolved in a polar solvent. For now, I'll be strict on that, but I think that makes sense. Ne? Then because there's an increase in hydronium ions, H plus ions, there's conversely means in reverse. Ne? Conversely, there's a decrease in OH minus ions, but that means then for bases there's an increase in OH minus ions. Ne? And then acids also decrease the pH of a solution. So pH is less than 7 for acids, and for bases, pH is greater than 7. So can you see just from those two? Yeah, I had why is it not refreshing here now? Because I want to would you the correct slide, but I'm not seeing it refresh, But I understand this thing in a low jumper and trick. Yo, now I'm taking time, just fixing technology. What's wrong with you? There we go. Yeah, ne? So are you seeing there's a link between, there's a relationship between hydroxyl ions and pH? So maybe we can question that. Is there a relationship between presence of hydroxyl ions and pH? No one? So in fact, you can say, is there a link between not just hydroxyl ions, the hydroxyl ions and the hydronium ions? So I'll just bracket it like this and put in H plus and OH minus. Because the hydronium ions, the hydroxyl ions increase and the pH also increases. But the hydroxyl ions increase and the hydroxyl ions decrease and the pH also decreases. That one. Then yeah. So back now to Arrhenius. Ne? Arrhenius theory is that for acids, Arrhenius, and then there's who? Bronsted-Lowry. Ne? So Arrhenius ori acid releases H plus ions, ne, in aqueous solutions. Remember, solution means a substance has been added to a polar solvent like water, and then it's formed an electrolyte. That's what aqueous means, ne? So acid releases H plus ions in that solution. So in other words, acids increase concentration of H plus, ne, in the aqueous solution, which means it's this reaction here. Hydrochloric acid becomes H plus plus Cl minus, or it's also HCl plus water, where water acts as a base. Then this becomes H3O plus Cl minus, ne? Because the water kind of receives into and then kind of receives like a H plus hydrogen G. Then a base releases OH ions, meaning sodium hydroxide can become sodium plus OH minus. So that's the Arrhenius model. And then the Bronsted-Lowry has a different has a different approach, but we'll discuss it now. Bronsted Lowry ore acid is a proton donor. Proton donor. And then it's also, I guess, it reacts horizontally. The other one, HCl plus H2O, is H3O plus Cl minus. So it's the same reaction. And you can apply that with, like, let's say this is an ammonium proton. No, sorry, it's an ammonium ion. Once you mix it with water, then it becomes H3O plus ammonia. And then the base, Leona, is a proton acceptor. So because it's a proton acceptor, its goal is so that it can combine with the proton to give you H2O. Or when ammonia reacts with water, then it gives you a hydroxyl ion plus that ammonium ion, positively charged ammonium ion. Ne? And what these basically tell you, Gore, base is a confirm the thing, yeah, base releases ions, ja OH, because the OH ion is released there. But now, this is just for acid-base theories. There's another one, yeah, the reactions with water, where acids ionize in water, they become ions. So they ionize, they become ions in water to produce hydronium ions. Ne? So the H3O minus is H3O plus rather is hydronium ion, and OH minus is hydroxyl ion. Ne? Yeah, so an example here, these types of questions would be multiple choice, where which of the following is a property of an acid? Decreases H3O, decreases OH minus, so decreases hydronium ion concentration in solution, or decreases hydroxyl ion concentration in solution. That's property of acid. Ne? Does it increase hydroxyl, or does it increase pH of solution? So we start first with the first two that we can eliminate. The two that we can eliminate, does an acid increase hydroxyl OH ions? No, it decreases them. Eliminate. Does an acid increase the pH of solution? No, it decreases the pH. Eliminate it. So we're left with just A and B that we can choose from. Now we have to be clever with identifying how they play with the English to confuse us. And we start by saying, we're looking at the property of an acid. Acid increases the hydronium ion concentration. So it definitely can't decrease hydronium ion concentration. So we eliminate A. That means we're left with B, which says acid decreases hydroxyl ion concentration in solution. Oh, it looks like it's just about right. So that's how you answer it. Now one. Start first with two that you can eliminate that are very incorrect at the bat, and then you look at the two that you have to be careful with. The second question asks, explain how a weak base differs from a strong base. So weak bases, weak base, no? Yeah, weak base. Okay. So do you have like somewhere in your notes where they compare acids, the strengths of acids between weak and strong, and the strength of base between weak and strong? You have somewhere in your notes so that we can explain that, because I'll have to open it to export here. Oh, let's look at Siyavula grade 12. You have that there? Okay. All right. Acids, bases. We're looking at the differences, weak and strong bases, ne? Okay. Strong base, ne? Yeah, I'm looking at weak acids. Strong and weak acids and bases. All right, cool. A strong acid, there is one that almost completely dissociates to form ions in solution. So that means a strong base would be a base where it doesn't dissociate completely. Ne? So the difference between a strong base and a weak base, as well as the difference between a strong acid and a weak acid, is how much do they dissociate when they're in solution. Dissociation is this process of going from HCl to H plus Cl minus. That's dissociation. So in other words, the other molecule, not molecule, the other atom dissociates from the other atom even though they were originally together. That one, they dissociate. So it's like the opposite of associate. Like that associate is to, but dissociate is to go in the other direction. So, oh yes, new slide. Okay. So, okay, question 7.2. Strong base versus weak base, ne? So weak base, so strong base rather, dissociates completely. in solution, but weak base partially dissociates. So partially dissociates in solution. That's the long and short of it. That's why it's like 2 marks. Alright. And then we have to write down the balanced equation for the hydrolysis of that's 7.3, ne? So they want us to write down the equation that's balanced for the hydrolysis of sodium bicarbonate or sodium hydrogen carbonate. Sodium hydrogen carbonate or sodium bicarbonate is the same one that you use in, I guess, cooking or other things that are household cook salt. Yeah. So the hydrolysis of it, what is hydrolysis? Do you know what hydrolysis is? Lyrics, okay. It's fine. We're gonna look for hydrolysis. Reaction between something and what hydrolysis. Salt hydrolysis. All right. So hydrolysis. Oh yeah, sodium hydrogen carbonate is a salt, I believe. Is a salt. Okay, so we're not far. All right. Let's do this now. There's a reason why they put sodium bicarbonate there. It is a salt. So you are right. Salt hydrolysis. Does neutralization mean that the pH of a solution is 7? Not really. At the equivalence point of a reaction, the pH of the solution need not necessarily be 7. This is because the interaction of the salt and water is like that. So at the equivalence point of an acid-base neutralization reaction, there is salt and water. The ions of water interact with the salt present and form a small quantity of excess hydronium ions or hydroxide ions. This leads to the pH values that are not equal to 7. A simple rule to determine the likely pH of a solution is as follows. So if we have a strong acid plus a strong base, they form a neutral salt and a water solution. So strong acid plus strong base will give us. So let's look at hydrolysis, man. So strong acid give us neutral air salt plus water, né? And then a weak acid plus a strong base. Or let me rather do this. Let's make it a table instead. So we've got acid column, we've got base column, we've got the salt and the water, né? So acid, base, salt, water. Ne? So if we have a strong acid, so acid that is strong and a base that is strong, they give us a neutral salt, ne? And a neutral a water solution, ne? Ne? But if we have a weak acid and a strong base, ne? They give us a weak base. So I guess yellow is closer to red. So they'll give us a weak basic salt, ne? So the salt will be weak, but it will be closer to a base in pH. And then we still get water solution. So the neutral ones will just keep. So these are the rules that we need to keep in mind to answer questions like that. NHCO3. If we have a strong acid, mara we have a weak base, ne? We will get a weak acidic salt and we will still have a water solution, ne? So we first need to check a substance, ne? There's approximate pHs here. That's interesting. Approximate pH. There's approximate pH. I think we should note that. Leaders, we should note that. Approximate pH. I should reduce this column altogether, actually. Reduce it so I can increase the number of columns. Ne? And then there's pH. Ne? So we'll have water solution. And then the pH, the relative pH here would be 7. And the relative pH for the weak basic salt would be 9. And the relative pH for the weak acid would be around about 5, close to 5. Ne? So that means if we're given a salt, we need to check the origin of the salt. What reacted before to give us that salt? Because if we know what reacted before, then we'll be able to tell if it's a strong acid, a weak acid, or strong base and a weak acid reaction. Now one. So now we go back. Let's look at sodium hydrogen carbonate. Ne? What reacted to form sodium hydrogen carbonate? You think we can find that in our books? Okay, so the salt sodium hydrogen carbonate gets becomes hydrolyzed. It reacts with water, ne? Or should I rather say, yeah, this one becomes NaHCO3 plus H2O, ne? So then this probably becomes salt, sodium bath. Oh no. Oh, check this out, man. So you see this table here? The HCO3 part, we can regard it as a conjugate base. So that would be the acid. So, wait. Wait, before I mislead you, I don't want to mislead you. I want to open something here. I want to see something. What they're going to share as question 7, Alright, I just want to refer to something because I got stuck on it's gonna take a bit of time to finish loading. So question 4 loaded, question 5 loaded, 6, 7, question 7. What about 28? Okay. Alright, question 7. Alrighty. So yeah, the HCO3 aqueous plus nitric. Then okay. So the HCO3 minus plus H2O. I can probably check hydrolysis. Okay, this should give okay, so this will give H2CO3 plus OH minus. Right, and these are aqueous. These are aqueous. Okay, but the long and short of it, the bicarbonate ion acts as the conjugate base, and the H2O will act as an acid, or rather acts as a conjugate acid, whereas the bicarbonate ion acts as a base. This one will act as a conjugate acid. So then the end result would be, because an acid I get it as the H2O conjugate base, and we said bases, they okay. Yes, bases, they increase the presence of hydroxyl ions, OH ions. So that means the HCO3 will receive a proton. Oh, okay. What's that thing I just saw now? Yeah, I'm free. Is it amphiprotic Yes, that thing. Wait, what? Interesting. Yeah. I want to share. What do I want to share today? For this one, not really. No, not titrations. What am I looking for here? Previous. Okay, start here. Okay. I'm looking for these definitions, ne? Ja, poking, amphiprotic, and what's the other one? Is it ampholite? No, not ampholite. You know those words I'm talking about, ne? Amphiprotic. I saw them just now. Or maybe I saw them in this book. Yes, I think I saw them in this book. Yeah, it's ampholite or amphiprotic. So ampholite refers to whether it can act as a base or acid, but amphiprotic means whether or not it will donate or receive a proton. So in this case, water is a amphiprotic. So in this case, it is a conjugate base, meaning it's a conjugate acid. So it donates a proton. So when it donates a proton, it becomes hydroxyl ion because the bicarbonate ion is a base. Ne? So this is a base. Or let me write that in blue. This one becomes a base. And this one becomes the acid. Ne? Because it is a ampholite. Ne? Yeah, the H2 is an ampholite. So in this case, it will act as an acid. And when it acts as an acid, it means it donates a proton. Now, upon donating a proton, we have an increase in hydroxyl. Ne? Increase. And when we have an increase in hydroxyl, it confirms the thing here. It confirms the acid-base theory. Bases decrease the H plus ion and increase the OH minus ion. Yeah. And then yes, so that's what we have. So to answer that question, NaHCO3 will give us a bicarbonate ion, which is in aqueous form, and we have to mix it with water, which is liquid form, and this reaction gives us H2CO3 plus, this is aqueous, plus OH minus, which is also aqueous. So that answers that question. Okay. A learner wishes to identify an element X in the hydrogen carbonate. To do this, the learner dissolves 0.4 grams of XHCO3 in 100 cubic centimeters. So this one goes to Chilachadi concentration. Ne? Okay, so we're starting here. Titration. Okay. 0.4 gram of the carbonate in water. So I think she makes a standard solution. She then titrates this with a solution of 0.2 mole per dm cubed of hydrochloric acid solution. Methyl orange is used as the indicator during the titration. There's specific types of indicators. Indicators just point to us what we're dealing with. Is it an acid? Is it a base? And what's the pH range of those things? Ne? And it's basically this. So this one, which is a test for whether we're dealing with a strong acid-base reaction or weak acid, strong base reaction, or strong acid, weak base. If we work with this, we'll get more or less stuff that's in that range. So on the pH scale, strong acid and strong base, you would looking at the colors here, which, let's look at it this way. So it would be 6.0 to 7.6. And then if we have a weak acid and a strong base, it will be between 8.3 and 10, so somewhere there. Now, and then strong acid and weak base, bromocresol green, so it will be between just close to 4 and just above 5. So that way we are looking for strong acid and weak base products. Alright, and then that's what we titrate with. Ne? I think that's what we use also in the titration. So this is how they look. The bromothimal blue, because it's for strong base, strong acid reactions, at the end of the reaction it will be green, but if we have more acid we'll have yellow, and if we have more base we'll have blue. Phenolphthalein, if we have an acid it will be colorless, but at the end, or if we have just the base, it will be pink, and then at the end of the reaction it will be faint pink. And then this one is almost like bromothimal blue. Bromocresol green is almost like bromothimal blue. So if we have just the base, it will be blue. If we have just the acid, it will be yellow, but at the end of the reaction it will be green. Alright, and then titrations are neutralization experiments, reaction, because if an acid solution of known concentration is added to a basic solution of unknown concentration until the solution is exactly neutralized, there's only salt and water, then it's possible to calculate the exact concentration of the unknown solution. So you can use a known concentration of one solution to find the concentration of an unknown solution. Ne? And how we do that, I think this is a concentration, mole per dm cube. The other one, we just have the mass and the volume of the mass of the substance that's mixed and the volume of water in which it's mixed. Then the titration happens with a acid of a concentration 0.2 mole per dm cubed, and the methyl orange is used as an indicator during the titration. So this is a weak base, that's a strong acid. Ne? Hydrochloric acid, we know it's a strong acid. And we know if we have strong acid and weak base, we will have a weak acidic salt. So our salt will have a pH around 5 or so. And then the other thing we know about methyl orange. Methyl orange is the best indicator because it's close to the pH range. Alright. So now we must find the pH of the hydrochloric acid solution. This one we are doing like this. The pH of hydrochloric acid solution, right? It'll equal minus log of the hydronium ions, H3O plus, and we need to okay. Under the 0.2, it's okay. Concentration, yes. Oh, okay. Cool. So we look at the concentration of the hydronium ions. And we're given that concentration of hydronium ions equals 0.2 mole per dm cubed, ne? So negative log of 0.2, and that gives us 0.7, give or take. That's the pH, ne? So that means it's a very, very, very strong acid, right? Very strong acid with a weak salt. Give a reason why the methyl orange is a suitable indicator in this titration. So it's a suitable indicator in the titration because is a suitable indicator. Okay, let's see the reason here. Titration of a weak base and a strong acid, I guess, because weak acid, weak base and strong acid will give you weak acidic salt. So methyl orange would be ideal because you'll have a weak acidic salt whose pH is around 5, and that's what methyl orange is good at identifying. Yes. At the end point, the learner finds that 20 cubic centimeters of the acid neutralize all the hydrogen carbonate solution. The balanced equation is something chlorine plus carbon dioxide gas plus H2O element. So we need to identify the element X by means of calculation. Interesting. Okay. There's two options. Alright. Okay, this one, you know those calculations, concentration, right? Those calculations, concentration. Alright, and the first thing that we need to take note of is that we have to quote the correct formula. So Renal concentration equals number of moles divided by volume. Renal number of moles equals the mass divided by the molar mass. We've got the concentration of acid times the volume of acid equals the number of moles of acid. And if you divide on either side by a concentration of base times volume of base, you equal you can divide throughout by Jela. Yeah. So in one of these formulas we need to be sure to use. We need to substitute the correct concentration, mole ratio, okay, number of moles. So in our reaction, we've got 1 mole, 1 mole, 1 mole this side, and 1 mole, 1 mole this side. So acid to 20 reactor 1:1, giving us 1:1:1 products in the end. All right. And then the other thing, okay. So this is the process we're gonna follow. So now let's do it. So now let's do it. So the first things first is our concentration of hydrochloric acid. Ne? So let's start with concentration of hydrochloric acid. Ne? It's gonna equal number of mole over volume. Ne? And we know that the concentration of hydrochloric acid is 0.2 mole dm cubed. And at the end of the reaction, only 20 cubic centimeters of the acid. So we know the volume of acid that neutralized all of the weak base. So we can say then concentration yantric is 0.2 again. And then the number of moles we don't know, but we know the volume, and it's 20 times 10 to the negative 3. So that's the conversion from cm cubed to dm cubed. We go from 1 is to 10 times to the negative 3. Ne? Then the concentration of acid, the number of moles rather, will be, therefore number of moles is going to be 4 times 10 to the negative 3 moles. Ne? Moles is important, that's the unit. Then we're going to take the concentration, or the number of moles rather, of the salt, the hydrogen carbonate salt, and it equals the number of moles of the acid. So number of moles of acid equals number of moles of base, right? Because from our reaction, X HCO3 plus HCl gives us XCl plus carbon dioxide gas plus water, which is liquid. Ne? So Havana, we've got 1 mole and 1 mole of acid. Ne? So which means 4 times 10 to the negative 3 for the acid will equal 4 times 10 to the negative 3 for the base. But we know that the number of moles also equals the mass over the molar mass. So the mass, what is the mass of the salt that was used before? It was 0.4 grams. Ne? It was 0.4 grams. And then we don't know the molar mass. So we can multiply throughout with multiplicative inverses. And the molar mass will be 0.4 divided by 4 times 10 to the negative 3. And that will equal 100 grams per mole. Ne? So that's the molar mass, 100 grams per mole. Now we're going to take this molar mass of the molar mass of X. Oh, okay, cool. So we must now find the molar mass of HCO3. Ne? We must find the molar mass of HCO3. And what does that equal? On our periodic table, it's 1. Carbon is 12. And oxygen is 16. So we multiply that by 3. So it's 30 plus 18, so it's 48. Ne? And this equals, that is 60 plus 1, which is 61 grams per mole. You see? 61 grams per mole. So then the molar mass of HCO3 should equal the molar mass of the X element plus the molar mass of the HCO3 part. We know that the molar mass of this is 100, of the chemical itself is 100 grams per mole, but we don't know mx, the element that we don't know, but we know the molar mass of the HCO3, and that is 61 grams per mole. So now we can just do additive inverses, and the molar mass of the X element is 39 grams per mole, and this tells us that it's potassium, because potassium on the periodic table is 39. No, the other ways I guess you can do it, but yeah. Yeah, I'm so sorry I'm not able to show up the way you had thought I would for your exam tomorrow, ne? But I definitely guarantee you, when we do our program going into the next week, come end of year, we'll be feeling much different at exam. And it's better we plan 2 terms, or rather a term before the term exams, than you try and do this day, but it doesn't work, and then last minute you come and you say, Mr. PR Tushan, because I don't know how to show up when it's just sudden like that, but I